Okay, so the next topic we're going to talk about is rheology. Rheology is the study of the flow of material. Another way to look at it would be the study of the relationship between stress and strain. We're going to be using these abbreviations, sigma for stress and epsilon for strain. We'll continue to be using those. Okay, so we're situated to think about rheology now that we've talked about stress and strain. And this is just a sort of a brief introduction to the idea. And we'll start with what we call elastic behavior. So in elastic behavior, stress equals some constant times strain. And the sort of the diagram to think about this as a graph of stress times strain. And pretty much if we apply a stress, we get some strain. And if we're going that way, we're loading the system. And then if we unload it, if we release the stress, head back down, that's unloading. And if we release all the stress, we end up right back where we started. So basically, no strain happens after we release the stress. This would be just for elastic behavior. We're not talking about a lot of strain usually, maybe 1%. So for elastic behavior, underline that. For elastic behavior, we get all the strain back. It's undone when we let go. So we call this recoverable strain. And this isn't really, we're not really talking about this kind of strain much, just in this class. But it's important just to have this as a reference. An example of this, of elastic strain, is seismic waves. So seismic waves travel through all sorts of rocks, and the rock looks the same before and after. It hasn't really changed, but there's been a pulse of strain that's gone through it. But one important concept here is that the slope here will not always isn't the same for all rocks. So the slope is what we call a modulus. So some things you apply a little bit of stress and they really deform. That'd be something down here. Other things you have to apply a tremendous stress to get any little strain at all. Okay, so that quality of the ratio basically is the modulus. We'll be talking more about permanent deformation. So maybe another analogy we could use here would be a paperclip. If you kind of lightly bend a paperclip and let go, it snaps back to how it was before. That's elastic behavior. But you can also take it and really kind of crank on it, and it won't go back. It'll be permanently deformed. So that most of the rocks, most of the strain that structural geologists are talking about is that sort of permanent deformation. So we're going to talk about sort of 3 general types of permanent deformation. All of them, we imagine sort of a lab experiment that can be done, where you take a cylinder of a rock, you apply a stress, a major stress, and then there may also be a confining pressure around the sample, and then different things can happen. So in one case, we have what we call brittle deformation. And whenever I draw sigma 1, there's an implied balancing. It's implied here that these are balanced, otherwise this thing would be moving. Or we're talking more about deforming it. So for this first case, which we call brittle deformation, we get fractures, we get cracks. So we get both fracture, and if there's motion on a crack that's already there, we have friction. And if we turn up the temperature a little bit and do the same thing, squeeze our sample, get sort of a similar geometry, but it tends to be more sort of, here we had these fractures happening at about 30 degrees to sigma 1. Here we get a similar sort of geometry, but there's a more spread out kind of deformation. So we're going to just, in our 3 cases here, we're increasing temperature to the right. So this is what happens when things are a little bit warmer. We call this brittle ductile. So this is localized, so it's not spread out. This deformation isn't spread out throughout the whole sample, but the deformation occurs, flows in domains. So there's sort of a zone of where the deformation happens. And then our third case, the whole sample is sort of smushed, sort of relatively homogeneously. And that's what happens when the temperature gets the hottest, and we call that ductile. Which means that there's a substantial change in shape without macroscopic fracturing. Okay, so there's no obvious plane or zone that allowed this deformation to happen. And the total strain in all these cases could be the same. It's just accommodated by different mechanisms, fracture and friction, or localized flow in domains, or flow distributed throughout the entire sample. So here's an example of a pebble that has been deformed in a with a fracture or several fractures. There's a main one here. You can also see some other ones. There's one coming down like that. So this would be friendly closer to the sort of brittle behavior. It's basically like a little fault cutting across this rock. There are a couple of them working together to strain this. And I'll go back to this outcrop that we looked at previously. These guys, these pebbles in here look pretty smooth. I don't see little faults in those. So this would be much closer to a ductile deformation. In fact, the way that all these rocks and this whole everywhere we look here, there's deformation. It would definitely be in the ductile realm. We've got a little bit of a, this is interesting here, I'm just noticing this vein cutting across. Here's another one up here. So it looks like there's a little bit of an interesting geological story here. After this whole area was strained ductily, looks like there was some kind of intrusion of a maybe a granitic melt that cut across a crack. Anyway, that's not the focus today. Here's another one cutting across. So there would be a story here of deformation of the conglomerate, strain, ductile strain, and then some fracturing and filling with a vein or a vein material.